If you've ever tried to re-edit a video and spend hours hunting for the exact frame where a cut happens, well, you know exactly how tedious it is. Welcome to this explainer. Today, we are unpacking a really exciting breakthrough in how AI interprets video editing. It's a brand new model called OmniShotCut, and it completely reformulates a classic problem in computer vision, shot boundary detection. Seriously, if you care at all about automated video generation or high-level video understanding, you're definitely going to want to pay close attention to this architecture. So, let's dive right into this fundamental question to understand the actual mechanics behind state-of-the-art video processing. When an AI processes an edited video, it basically needs to break it down into its most atomic temporal units, and by that I mean a single unbroken shot from one camera angle. But detecting exactly where one shot ends and another begins is surprisingly difficult for traditional models, especially when you throw in artistic transitions or really subtle cuts. Now, there are four major hurdles that legacy models face. First, notice the complete lack of relational information. A traditional model might detect a boundary, but it has absolutely no idea if it's looking at a dissolve, a fade, or a wipe. Second, they constantly neglect tiny continuity jumps, what we call sudden jumps. This happens when an editor crops out just a tiny segment of continuous footage. It causes an abrupt motion discontinuity that old models completely miss. Third, ambiguous transition boundaries are just incredibly difficult mathematically. The pixel values between two scenes blend gradually over dozens of frames, so pinpointing the exact start and end frame is a nightmare. And finally, existing benchmarks are just completely outdated. They lack the domain diversity needed to train modern systems. Okay, here is our roadmap for today. 1. The baseline problem. 2. The shot query transformer. 3. Encoding space and time. 4. Decoding with shot queries. And 5. Optimizing range and relations. Let's jump straight into section 1, the baseline problem, and exactly why standard methods fall short. So traditional methods like Transnet V2 or AutoShot are pretty limited because they simply can't classify editing transitions. They just hand you a temporal range, completely lacking any transition interpretability. Plus, to process long video sequences efficiently, these legacy models rely heavily on 3D convolutional neural networks, or CNNs. Now, to keep compute and memory from absolutely exploding, 3D CNNs require really aggressive spatial downsampling. But here's the catch. Because they compress the visual data so heavily, they completely destroy the fine-grained pixel tracking you need to spot those subtle, one-frame sudden jumps. Basically, these architectures just aren't built for structured, relational prediction. Moving on to section 2, the shot query transformer, which is the anatomy of a real breakthrough. You can think of this new model as a highly specialized assembly line. Step 1 is the image encoder, specifically a resonant backbone, which encodes the raw video frame by frame. Step 2 is the transformer encoder, where those spatial and temporal dimensions are literally flattened out. So the raw video transforms from a 3D sequence of images into a 1D mathematical sequence of tokens. And finally, step 3 is the transformer decoder. This uses a set of fixed-length learned queries to decode that dense 1D sequence back into optimized, explicitly labeled shot segments. Let's look closer at section 3, encoding space and time, where we prepare the tokens. To understand the first phase of this assembly line, we need to look at how the model tracks the spatial, temporal coordinates of every single frame using 3D position embedding. Since we're shifting from static images to moving video, standard 2D coordinates, just X and Y, aren't going to cut it. The model generalizes these to 3D coordinates, time, Y, and X. By applying sinusoidal embeddings, which are essentially wave-like mathematical functions, along these axes, the system gives every single pixel a completely unique timestamp and coordinate. This is what allows the transformer to seamlessly model joint spatiotemporal relationships. And this 3D embedding is absolutely critical. Why? Because transformers, by their very design, process tokens in a permutation-invariant way. They don't inherently know the order of the incoming data. So by injecting this precise 3D mathematical blueprint into the flattened video tokens, the model ensures the video retains its perfect chronological and spatial layout without getting all mixed up, no matter how long the sequence actually is. Which brings us to section 4, decoding with shot queries. This is where we gather the evidence. Once the video is mapped and embedded, the data flows into the transformer decoder. This introduces the core innovation of the whole architecture, shot queries. These fixed-length trainable embeddings act like individual worker baskets. They're preset prediction slots. So instead of just blindly scanning the video sequentially and guessing where a cut happens, each query actively gathers specific visual evidence for one specific shot. They're essentially learned mathematical vectors that refine their focus over multiple layers, pulling all that dense temporal and spatial data into one compact hidden state. In every decoder layer, these worker baskets go to work. First, they undergo self-attention. This literally means the baskets talk to each other to make sure they aren't predicting overlapping shots. They're basically saying, hey, I've got frames 1 through 50. You take the next batch. Then they perform cross-attention with the original encoded video tokens, cross-referencing the actual timeline. Finally, and this is a huge compute-saving breakthrough, they predict a dedicated termination token. The exact moment the model hits the final cut of the video sequence, that token says stop. Any queries after that are just discarded, which saves an incredible amount of processing power. And finally, Section 5, optimizing range and relations through the output heads. So the queries reach the end of the line, and the collected evidence has to be translated into exact editing cuts. This requires a massive shift in output logic. Older models use continuous regression, basically trying to guess floating point numbers to draw a boundary box. But in video, guessing a floating point number is dangerous. A one-frame deviation at a hard cut is a huge error. You can't be sort of on the right frame. So OmniShotCut completely discards continuous regression. Instead, it formulates range prediction as discrete classification. It treats every single frame index as a distinct, discrete class, which lets the model pinpoint the exact cut frame with zero deviation accuracy. To achieve a really holistic understanding, that unified hidden state is passed through 3 parallel output heads simultaneously. Because they share weights, they actually optimize together. The range head predicts the discrete temporal boundary, the exact end frame. The interrelation head looks inside the shot to classify the transition type. Is it a vanilla segment, a wipe, a dissolve, or a fade? Meanwhile, the interrelation head distinguishes the relationship with the preceding shot, explicitly classifying whether the cut was a standard transition, a hard cut, or one of those really tricky sudden jumps. And the results? They are stunning. Because of this discrete classification and those highly optimized parallel relational heads, OmniShotCut reaches a transition intersection over union, or IOU score, of 0.632. To put that into perspective for you, standard state-of-the-art models in the literature struggle to even hit 0.25 on the exact same datasets. That's not just some incremental update. We are talking about a complete paradigm shift in accuracy. When you look at the visual proof side by side, it really grounds the math. Take a scenario with a gradual fading transition, where pixel values blend over dozens of frames. Legacy models like Transnet V2 and AutoShot predict entirely misaligned boundaries because it's so hard to match the ground truth. OmniShotCut, however, flawlessly matches the ground truth on the right. And in a video with a tiny sudden jump, the legacy models output a continuous, unbroken timeline. They miss it entirely. But OmniShotCut catches the jump perfectly. This shot query transformer captures pixel-perfect boundaries where older architectures completely fall apart. And that leaves us with a pretty fascinating final thought. We know that AI requires perfectly continuous sequences to train video generation models without spatial glitching. So if this shot query transformer can so precisely decode the most atomic temporal units of a video, catching every fade, every cut, every tiny sudden jump, what does this unlock for the future of large-scale AI creation? Understanding exactly how humans edit might just be the ultimate key to teaching AI how to seamlessly generate reality. Thank you so much for joining me for this explainer.